So what kind of answers are you getting here? 10? Did everybody get 10? Anybody get something else? 8. Anybody get anything else? All right, so those are usually the 2 answers I get. So how did you get, somebody tell me how did they get their answer? The area of the top one minus the area of the bottom one. How did you find those areas? Okay, so you kind of split it up, something like this? Okay, so then for each of these shapes, you can use the area formulas for these shapes. So 1/2 base times height here would be 2 times 2 would be 4, and half of that would be 2. And here we've got 3 times 2, so that's 6. This one's 1, and this one's also 1. So now the question is, if we add all those up, we get 10. But that's not right. What are we supposed to do with the very last one here? Subtract it. And why do we subtract it? Yeah, so it's below the x-axis, right? That's the simplest way of saying why we subtract it. So anything above the x-axis is positive, below the x-axis is negative. So that was the main thing I wanted to remind you of, that when we're doing area here, it's not really area. It's what they call signed area. So now we're going to talk about the first fundamental theorem of calculus. So what's going on here? Well, we know how to calculate the integral from a to b of something, right? That makes good sense. So then the next question is, does it make any sense to calculate the integral from a to x? Is that the same thing? What would it mean to you if we said the integral from a to x? You think that's the same or different as from a to b? So yeah, you're just changing the letter. So there's an argument to be made there that, you know, it's algebra, right? It doesn't matter what letter we use. But do we mean the same thing? When I put the b up here, is this supposed to be a constant or a variable? It's a constant. It's something given to you in the problem. They give you your function. They give you a and b, and you're supposed to interpret that as this area. Over here, we want to think about x as a variable. So what does that mean? That means that they've given you your function, they've given you a, you know where you start? But then you've got like a little sliding piece over here where you could be finding this area or this one or this one. I can do a much better job of this with an applet than I can with my own drawing. Let's see what we got here. Cross our fingers here. There we go. So with this applet, it's the integral from 0 to x. So the a side starts at 0, but then we can move the x. So see, if x is 2, we're finding this area. If x is 4, we're finding this area. If x is 8, maybe we'd be finding this one. Does this make some sense to you? So we can actually think of this as a function. We can call it capital F of x, and depending on the different values we put in for x, we'll get different integrals from a to b. So that we'll get different areas. So it's a function where you put in the b value, and you get out the signed area. Does that make sense? Okay, so the reason we're doing this is that this function is actually kind of special. So if we go back and we look at the applet, the red graph over here on the left side is the graph of the area. So let's see if that makes sense. So here, as x gets bigger, my area is getting bigger, right? And then what's going to happen when I cross this place where the original function crosses the x-axis? What's going to happen to my total area? It's going to start getting smaller because I'm taking away this area that's under the x-axis, right? And then once I get to this point, what's going to happen? It's going to start increasing again, and then it's going to start decreasing. So does that make sense? Okay, now we're going to do something kind of weird. We are going to think about the rate of change of this red function. Because this red function here, this capital F function, this is the one we're interested in. We want to think about its rate of change. So we want to think about how fast it's growing. Is it growing faster or slower? And what is helping us, what determines whether it's growing faster or slower. So right here at the beginning, when I move x just a little bit, I'm adding a lot to my area, right? Because it's really tall. Versus over here, x is, the original function is kind of short, so I'm not adding that much area when I need x the same amount. Do you see that? And over here on my area function, this is reflected by the fact that at the beginning it's very steep. But when I get here close to 0, it flattens out. I'm not adding nearly as much area. The rate of change is not as big. Do you see that? So now if I become negative, I'm going downhill now, but when the height is close to 0, I'm still not adding that much. I'm adding more over here. It's steeper. The red curve is steeper because the blue curve is farther from 0. And then it flattens out, and then it gets steeper and less steep. Do you see that? So what are we saying? We're saying that the height of this blue function corresponds to what on the red function? The higher the blue function is, what can you say about the red function? The steeper it is. Okay, good. So the height on the blue function corresponds with the steepness of the red function. So height, how do we say height? I mean, this is the function little f. Is the height the x value, the y value, the derivative? What is the height? The y value. Okay, so the height is y equals little f of x. What is steepness? That's the slope, okay. So it's the derivative? Yep. So this function is capital F, so capital F prime of x. So if we increase little f of x, we've increased capital prime of x. If we decrease little f, we decrease capital F prime. Is this making some sense to you? Okay, so what the first fundamental theorem of calculus says is that this number and this number are actually equal. That's what it tells you. And this might seem obvious because of the notation that we use, but it was actually a really big deal when they figured it out. They had no reason to think that, till they kind of played with this picture for a while, that the tangent line should have anything at all to do with area under a curve. I mean, would you think that just kind of off the top of your head? So that's what it's telling us. And in math notation, it looks like capital F prime of x, which is the derivative of the integral. But note the integral starts at a fixed a and goes up to a plane x of an original function, gives you back that original function. So it's saying that a derivative undoes an area. It undoes a definite integral. So note, there's two things to note. It absolutely has to have a fixed value for a and a plane x on top for this to work. And you're going to have started with some other variable, and it's going to change to the variable that's at the top of your integral after you do this process. It does not matter what a is as long as it's a constant. For example, the integral from 2 to x of t squared minus cosine of t plus 3 dt. I know you know how to find that integral, but that's not what I'm asking you to do. I want you to find the derivative of that integral. Because the theorem says if you take the derivative of the integral, you get back what you started with, but you've changed all the t's to x's. So this is just x squared minus cosine of x plus 3. That's it. Now, if we actually, let's see if this actually makes some sense. If we actually take this integral, if we get, they're t's, right? So t cubed over 3 minus, what's the antiderivative of cosine? Sine of t plus 3t. And we evaluate it from 2 to x. Let's see what is going to happen. We're going to get, this is all capital F of x, right? So capital F of x is going to be x cubed over 3 minus sine of x plus 3x minus 2 cubed over 3 minus sine of 2 plus 6. Is that right? All right, so now we want the derivative of that thing, right? So what is that? F prime of x. What's the derivative of x cubed over 3? X squared. What's the derivative of sine? Cosine. What is the derivative of 3x? 3. What is the derivative of all the rest of it? 0. These are all constants, so they all have a derivative of 0. So you see what we've done? We've done a bunch of work to get back to the same answer that we get from the theorem. So that's what it means when it says this is why it changes the variable, because you've plugged it in and then you've retaken the derivative. And that's why it doesn't matter what a is, because no matter what number you plug in, as long as it was constant, this term will be a constant and go away. So now what it gets tricky is when we start throwing in, well, what if it isn't exactly what they give you? What if you're going from x to 4? Can you fix that? Flip it and make it negative. Exactly right. That's one of the rules about integrals. So you make the integral negative, and then you put the 4 on the bottom, the x on the top. And now you've got it so that you're allowed to use this rule. It's constant on the bottom, plain x on the top. So what do you get? Negative 3 over x, and you're done. Not so bad. Okay, so where does it get tricky? It gets tricky if the number on top isn't a plain x. What do you have to do now? Multiply it by its derivative. Why? And I guess that's what the teacher said. What do you have to do with a regular function if there's something is supposed to be x but it's not? Say you had y equals sine of x, and you know how to take the derivative of that, right? What is it? So y prime here is cosine x. Now what if I change the x? So what if I say y was sine of x to the third? Now what would you do? Chain rule. So you're still going to get the derivative of the sine part, which was cosine. You're still going to keep that x cubed there, but then you're going to multiply by a 3x squared at the end. And that's what's going on here. This is why we're multiplying by its derivative on the end. Because we've just taken the place that's supposed to be x. Right here is supposed to be x, right? If you stick something else in there, okay, well that's fine. You can stick it in there, and you can take the derivative with it in there. But then you have to take your answer and multiply by that derivative. When we did this comparison with sine of x cubed, we had an inside function and an outside function, right? So when we had sine of x cubed, what was our outside function? Sine of something, and then what was the inside function? X cubed. And the chain rule says take the derivative of the outside function, plug in the inside function, and then follow with the derivative of the inside function. So for our integral here that we want to take the derivative of, what's the outside function? What's the inside function? The inside function is usually easier for people. What is the inside function? Yeah, x squared. It's the thing that was supposed to be x. It's x squared. So everything else is the outside function. So what is the outside function? What else is there left? So the t cosine of 2t is part of it, but that's not everything, right? If I take t cosine of 2t and I put x squared into that, do I get back my original? No. So I need t cosine of 2t, but I also need the dt. I also need the integral from 0 to, and then this is where it's weird. I just 0 to something, right? There's the blank. So this entire integral is your outside function. And when you take its derivative, you're taking the derivative with the fundamental theorem of calculus. So when you go to take the derivative of this integral, you get back what you started with. You get back something, cosine of 2 times something, because that's what the fundamental theorem says. It says if you're going from 0 to a variable, you get back the original equation, but you've changed the t's to somethings. So if I put, this is the integral from 0 to smiley face, I'm going to get smiley face cosine of 2 smiley face. Does that make sense? So, but instead of smiley face, I have x squared in there. So I'm going to get x squared cosine of 2x squared, and then I have to follow with the derivative of x squared, just like I did over here. This is the hardest one. There are shortcuts to these, like just little, you can memorize the answer, but I wouldn't do that because I don't know if you'll get full credit. So what you want to do is you want to use an integral rule. So you guys remember the integral rule? First of all, what's wrong with this one? Why can't I just use the theorem right now? It needs to be a constant, right? I've got a variable in both spots. So there's a integral rule that says if you've got a, b, c here, right, that, you know, the way you usually think of it is if you integrate from a to b, and then you integrate from b to c, you might as well have just done the whole thing, right? Well, we can use that here by making up a b. We've got the integral from x to x cubed. Let's just stick a constant in here. What's your favorite constant? 0 is a perfectly fine constant. It makes you happier to pick 17 or pi or any other constant you can. Whatever you like, just stick it in there. And it doesn't even have to be strictly between these numbers, so you don't have to worry about that. Just stick in any constant you want. You're going to integrate from x to the constant, and then you're going to integrate from the constant to x cubed. So that'll give you two integrals. Each of those you should already know how to do. So see if you can finish this problem on your own. I gave you guys a hint if you're having trouble.
The derivative of the top integral, or the top.
So did you start with by splitting it up from the integral from x to 3 plus the integral from 3 to x cubed? Every one of you had a 3. You had a 0. Does that matter? Whatever you want to put there. If you want to make this a 0, that's fine. If you want to make it a 30, that's fine. If you want to make it, I don't know, negative 12, that's cool too. So now each of these problems are like ones we've already done. So the integral from x to 0, how do you fix that? Make it negative. So this is now negative the integral from 0 to x of sine squared of t dt. And then the second one, I'm actually going to leave it just like this for now. It's when I go to take the derivative that I'm going to have to remember to use the chain rule. Oops, that's a t. Okay, so now I'm ready. This is my original f function. This is capital F. Now I'm ready to find capital F prime. So for this first equation, do I have to do anything special? Do I need to use any theorems or anything to take the derivative? It's just this theorem that we just learned, right? The first fundamental theorem of calculus. But it's going from 0 to x, so I'm cool. All I have to do is replace the t's with x's. Now the key here is that you've taken the derivative of that integral, okay? So this only works if you're taking a derivative of an integral. It's a very special situation. Now the second one, again, I have the integral from 0 to box. So I'm going to get sine squared of box. But what goes in the box this time? X cubed. And am I done? Now I got to follow it with 3x squared. This is it. This is all they can ask you about for first fundamental theorem of calculus. All right, so what's the second fundamental theorem of calculus? Well, this is one we actually have already used today. We just didn't even mention it. We just used it. So the second fundamental theorem of calculus is using antiderivatives to find integrals. So it's the other way around. It's the first fundamental theorem said derivatives can undo integrals. This one is going to say that antiderivatives let you find area. And so all you do is, if you want to find an area, find the antiderivative and plug it in from b to a. So this is about as easy as it gets. All right, we're going to take the antiderivative of 2x squared plus x from 1 to 3. We want to find that area. We used to have to do a Riemann sum. You know how to do the Riemann sum for this, right? So you could do that. In fact, if you really want to make sure all this stuff works, you could do it and then do the shortcut, see if you get the same answer. But what does the shortcut say? It says it's the same thing if you just take that antiderivative and you plug in the numbers from 1 to 3. So this line with the numbers on the sides there, that's your way of saying I'm planning to plug in the numbers from 1 to 3. It's an important step in the notation. You want to make sure you use it. You also can do, some people do little square brackets around it. That's also fine. But one of those two things. And then you plug in the top number first. So 2 times 3 cubed over 3 plus 3 squared over 2. Now this is where people make a lot of mistakes. You want to put that in parentheses, minus and other big parentheses, because this subtraction sign applies to every term that you plug the 1 into. So you get 2 times 1 cubed over 3 minus 1 squared over 2. So you should just always expect your answer to be of the form big parenthesis minus big parenthesis. And if the big parentheses aren't necessary, well, okay, you've written extra parentheses. What about the plus c? So let's do it for one time and see what happens. So let's do plus c from 1 to 3. So now I plug in my 3, and I end up with that. And I plug in my 1, and I end up with this. And now my next step, if I were going to simplify this, would be to distribute that negative sign. So I would end up with, I don't know, 18 plus 9 halves plus c minus 2/3 plus a half minus c. So what happens to the c's? They cancel, and they always cancel. It doesn't matter what your function is, you'd always get the same c on each of these terms, and so that's why we don't bother to put it. So it won't hurt if you put it as long as you remember that they cancel, but you don't have to remember it with these. What is the antiderivative of secant squared? Tangent, yep. So secant squared of x, the antiderivative is tangent. So since we know that, now all we have to do is write tangent of x evaluated from 0 to pi over 4 is tangent of pi over 4 minus tangent of 0. And you totally can stop right there. You don't even have to figure out what those numbers are. So are we ready for U-sub then? This is the interesting stuff to me. This is the stuff that's really kind of core. This is where it's kind of hard to understand what's going on, but once you do, it's really powerful. It's like one of the main techniques for finding integrals. And if you are going on to Calc 2, you're going to use this all the time. So you really want to make sure that you understand what's going on here. So U-substitution, what's going on? We want to find an integral. Say, for example, sine of x to the 4th times 4x cubed. And if you look at that, do you know the integral off the top of your head? You know the antiderivative of that? I certainly don't. Okay, so what we need to do is develop techniques for, hey, here's something I don't have the antiderivative memorized for, what do I do? And if you go on and take Calc 2, the first, 5 weeks of that class is going to be more techniques for doing this that get more complicated, but for you, this is like the main technique we're going to do is this U-substitution. And so it's not, the first thing to take away from that is this technique does not always work. It kind of feels like it at first because they always give you ones where it works. But it doesn't always work. But what are you looking for? When would you might do this kind of technique? You're looking for, first of all, multiplication. Are you allowed to split up an integral by multiplication? Does this make any sense? Okay. Yeah, that's really, really bad. If you've gotten anything so far about integrals, that's bad. You can't do that. So what do you do when you see multiplication? Well, we're going to remember that these are derivatives, right? We're trying to find an antiderivative, so we're assuming this is the derivative of something. So we had all those derivative rules that give you all kinds of complicated things, right? So you had, let's see, the product rule. So if you had f times g, that gave you f prime times g plus f times g prime. So that gave you stuff multiplied together, but it gave you extra stuff, right? So that doesn't really look like just two things multiplied together. You had the quotient rule, f over g, but that was f prime g minus f g prime over g squared. Does that look like this? Not at all. So there was one more, right? There's f of g of x, and that one went to f prime of g of x times g prime of x. So that one gives you just two terms multiplied together. You get this thing times this thing, where one of them's kind of ugly and then the other one's simpler. So is that what we have? We have two things multiplied together, one of them's a little uglier, one of them's simpler. So there's a good chance that this problem is a chain rule. The original problem was a chain rule and we're trying to undo it. So that when you think that that might be what's going on, that's when you want to try U-substitution. Because what U-substitution does is it's a technique to undo the chain rule. Does that make some sense to you so far? Okay. So the chain rule was so complicated to begin with because you have one function plugged into another. And this looks so ugly because you have one function plugged into another. So what we want to do to solve these kind of integrals is get rid of that second function. If we didn't have to look at the g, it would all look so much cleaner. So what we're going to do is we're going to change the variable. All right? So we're going to say, okay, well, this is all ugly. But if it was just plain sine, I would know how to do it. Right? So my smiley faces, where did my smiley faces go? If it's sine of smiley face, d smiley face, you guys know how to do that integral, right? So what we want to do is, unfortunately, smiley faces are hard to draw, so we call these things, now I'm writing in smiley faces. We call this placeholder a u instead of a smiley face. But we're gonna take our integral, and the goal is to do a substitution, do a change of variable, so that every time there's an x, instead it's written as a u. And if we can do that and get something simpler, then that's what we've done U-substitution. All right, so what do we want? We want to get rid of this x to the fourth. So we're going to call that u. Why is the x to the fourth the thing that's bothering me? Why do I want to get rid of it? Do you see this composition here? You've got one thing plugged inside of another. Like the time when if you were going to take the derivative of that, you'd have to use the chain rule, right? So whenever you have a composition like that, you have a function here where if the inside was a plain x, you'd know what to do, but it's not a plain x. That thing that you wish was a plain x, that's the thing you want to call u. And that's the thing you want to try to get the rest of the integral in terms of. So I'm going to replace that x to the fourth with u. So I'm going to end up with something like, sine of u. But now I have a 4x cubed dx still. So what do I do with that? Well, back on this previous page, sine of box d box we were good for, but the boxes had to match. So if you're going to change this one, you have to change the d dx into a du as well to make that match. Otherwise, you can't. It doesn't make any sense. And what this is doing, do you remember what the dx was on the picture? Way back here, we did like Riemann sums with rectangles. What was the dx measuring? The delta x. It was important, right? What was it for? It was the width, right? All these rectangles. Right here, this was delta x, and it became dx when we took the limit. So if I'm doing a change of variables, if this is x and this is y, and in on my new graph, this is y and this one's now u, and I don't know what it's done to my picture. I don't know, maybe it looks like that now. But one of the things it's done is it's changed this width. It now has to be in terms of u. So that's what you're doing. That's why it's really important to make sure this part's going to be the height, but this part's going to be the width of your rectangles. So how does this, what do you do? So we have to find a du. And to find a du, well, I know how to find du dx. What does this notation mean? Du over dx, what is that asking you to do? derivative of u with respect to x. So it's a derivative notation, right? It says treat u as a function, treat x as your variable. And if we do that, we take this function, we take u as our function, x as our variable, we get du dx is 4x cubed. You guys okay with that? But now I want to know what maybe just du is. So if I solve for du, this is the part that's really weird. I'm going to treat these du and dx's as actual things now, even though they're infinitely small. So I'm going to get 4x cubed dx. And now I want to do this substitution, so I need to match stuff up. And there's different ways of doing this matching. The key is just to always make sure everything changes. So if I'm starting with integral of sine of x to the 4th times 4x cubed dx, and I've already decided that this x to the 4th is what I want to call u, and I need to do something about this dx, I need to change it to a du. Can you guys see any way to make things match so that I can do that? See anything maybe the same on between these two equations? Anything that lines up? Du, the 4x cubed. So just this part, I should take that out and call that du. And the dx too. Okay, so I should take this whole thing and call that du. Because it matches exactly with this whole thing. Yeah, no, that's exactly right. So if we do that, our new integral is integral of sine of u du. That's what we're aiming for. And that one we know how to do. So what's the antiderivative of sine? Negative cosine of u. Do I need a plus c? Yes, there's no limits of integration, so I have to have a plus c. Alright, so one last thing. I started my problem in terms of x, so if I gave you this problem on an exam, I'd want an answer in terms of x. So how do I get back from what I have now to something in terms of x? I plug in u, so I already know u equals x to the 4th. That's what I said at the beginning. So I'm just going to get negative cosine of x to the 4th plus c. I can hide it, like I can make it so it doesn't look quite so much like that. Like if I had written it maybe as, let's just get a new page. If I had written it as this, then I have to actually put it together like that to get the du. So it's a little harder to see. And I could even give you just this. And the reason that would be okay is because constants can be pulled in and out of the integral. So if I need to stick a 4 in here, I can just stick a 1/4 out front. And it's still okay, and I can still find this thing I need. But if you can't find that thing you need, you can't do that substitution. I said at the beginning, you can't always use this technique, and you cannot use this technique when you cannot make it match exactly what you have in the du. Because if it doesn't match, that means it didn't come from a chain rule. Or at least it didn't come from that chain rule. So say this 4 wasn't here. There's a couple ways to fix it. But let's do the same problem, but without the 4. So say this is more like what you would probably see in your homework. I probably wouldn't set it up for you so easily. So we do that. We know that we want to get rid of this, so we let u be x to the 4th. We take its derivative. Du is 4x cubed. Now we know that's really du over dx, but once you've done a few of these, you can just skip straight to putting the dx on this side. And now I want to match it up. And I can find the x cubed I need, and I can find the dx, but I can't find the 4. So now I can show you 3 things to do. They all do the same thing. So one way to do it is what I just showed you. You can say, well, I need that 4. I'll stick it in, and I'll put a 1/4 out front. The second thing you could do, if you don't like that one, is, you can say, well, I have an x cubed dx. I'll just take this equation and solve it for the x cubed dx. So now when I substitute back in, I have sine of x to the fourth times du over 4 instead of just du. Does that make sense? The third thing you can do is say, I don't like thinking this hard. I am going to just always solve for dx. So I'm going to say to myself, du over 4x cubed equals dx. I'm going to stick that in where the dx was. And then I'm going to hope and pray that I can find some way to make all the x's cancel. This is dangerous, in my opinion, because you are tempted to make algebra that's not true happen just to make your x's go away. So I prefer one of the other two. But all of these things, and you end up in the same place with all of them, right? You all three, you end up with a 1/4 sine of u du. Questions about that? That's a really good question. Let's see what we're supposed to do next. When U-substitution fails, so this was exactly your question over here. Can I take the integral of sine of x to the fourth dx with U-substitution? Is this going to work? So I want to say, make this u, because I know how to do sine of u. U equals x to the fourth. Du equals 4x cubed dx. And no amount of rearranging that you do is going to make this x cubed disappear. There has to be an x cubed to cancel. So this is just no. You can't do this. You don't know how to solve this problem. Does that make sense to you guys? All right. There are two more things to notice about U-sub. This next one is called back substitution. You can sometimes force the U-sub to work when it doesn't look like it's going to work right away. That's what we're going to do here. So when I look at this, I know how to do 1 over u. All right? But I don't know how to do 1 over or something over if the bottom is complicated. And so this is one of the first things you'll always want to try if there's a fraction. Well, can I just let u equal the whole bottom? And see if I can make it into 1 over u. So if u equals x plus 1, what's du going to equal? dx. Well, that was nice and easy. I don't even have to worry about making that part match. But I end up with the integral of x over u du. So I haven't gotten rid of all my x's. That's bad, right? So should I just quit? In this case, I can actually force it to work. Because I know this equation right here. I know u equals x plus 1. And I have an x here that I want to get rid of. So can I take this equation and figure out what x should be? You know, I know what u is in terms of x. Can I find x in terms of u? What should it be? U minus 1. So in this particular case, the integral that I get now looks like u minus 1 over u du. Is that any better than the one I started with? It is better because of an algebra rule. What's better about plus or minuses on the top instead of on the bottom? Why do we like our plus and minuses on the top? You can break up the fraction. Here, you can write this as u over u minus 1 over u. Here you cannot, because the plus sign was on the bottom. Do you see that difference? So then you end up with the integral of 1 du minus the integral of 1 over u du. What's the integral of 1 du? U. So that's another key. Because this is a du, that du tells you the antiderivative of a constant should be u, or that constant times u. Whereas if there was an dx here, it would be the antiderivative would give you x. Does that make sense? All right, and then what's the antiderivative of 1 over u? ln of the absolute value of u. Don't forget those absolute values, plus c. And what's my last step? Change it back. So u is supposed to be x plus 1. So I have x plus 1 minus natural log of the absolute value of x plus 1 plus c. Questions on that one? So the key here is you can try to force it to work if you have extra x's. If they're in the integral part. If they're in the du part and you have no x's to match them up with, you're kind of in trouble. You can, I guess you could play around for a while and you can always like convert everything to u's, but it might be so ugly that it was much worse than you started with. The last one, what if you have numbers here? What if you have a definite integral instead of an indefinite integral? We need to use the fundamental theorem of calculus. How do we deal with that? Okay, so yeah, there's actually 2 completely different ways to do this problem. One is to ignore the 1 and 2 and say, well, the fundamental theorem of calculus says if I can find this antiderivative, then I can use it. So let's just find it. How do I do it? How do I find the general antiderivative of x plus 3 to the 60th? Do I need to do any kind of substitution? What do you think? Yeah, u equals x plus 3. Your other option is to FOIL out to the 60th power, and that does not sound like fun. So u equals x plus 3 du equals dx. So once again, these just match exactly. I don't have to worry about them too much. So this is integral of u to the 60th du. It's about as easy as you can get as far as a U-Substitution. All right, and so then I get u to the 61st over 61st plus c. So what I've done here is the general antiderivative. I've ignored the 1 and 2. And now that I know that, oops, I have one more step, right? What else do I have to do? I have to go back to x's, oh yeah. Okay, so one more step. What was it, x plus 3 to the 61st over 61 plus c. All right, so now I've found the general antiderivative. It's right here. And then, according to the fundamental theorem of calculus, if I want to do this definite integral from 1 to 2 of x plus 3 to the 60th dx, I know it's going to be a specific antiderivative, so x plus 3 to the 61st over 61, evaluated from 1 to 2. So now I can plug in the 1 and the 2. So I get 5 to the 61st over 61 minus 4 to the 61st over 61. The first way is to find what does the fundamental theorem of calculus say? It says, if you can find an antiderivative to this, take that antiderivative, here it is, and plug in 1 and 2. And that's what I've done. So but to do that one, you have to do this antiderivative without any numbers on it. You have to do it completely separate from the 1 and the 2. So this is the way of, I don't have to learn anything more, but it takes me longer. All right, the second way is to say, I want to convert everything. So I want to go the integral from 1 to 2, x plus 3 to the 60th dx. I still want to make u equals x plus 3. I want to make du dx, because I'm taking the derivative of x plus 3. And now I have an integral of u to the 60th du. But now I'm doing something different. Because now I'm not doing the general antiderivative. I'm doing the specific antiderivative from 1 to 2. And these numbers from 1 to 2, we go back to our picture. Here's 1 and 2. Here's our function. This is the area we're trying to find, and this is on the x-axis, right? So these are x values. This is x equals 1 and x equals 2 on the x-axis. So if we want to change our picture, this is now my u-axis, and whatever my function now looks like, I need to find these new values. What u numbers correspond to x being 1 and x being 2. So how do I do that? Plug it into the u equation. Right here I have a relationship between x and u. So I want to find u of 1, which would be 1 plus 3, which would be 4. That's my new a value. And u of 2, which would be 2 plus 3, which would be 5, that's my new b value. You see it? Now I can just do this problem and ignore the fact that it ever came from a previous problem. So now I get u to the 61st over 61, evaluated from 4 to 5. So 5 to the 61st over 61 minus 4 to the 61st over 61. Did I end up with the same answer both ways? Yes. So either one is fine, but this way of changing the limits is, if you look at the number of steps here, a lot shorter.